Hi, I'm Daniel Chan from UNSW Sydney. This is Extension 3 Mathematics for talented high school students. In this video, I want to talk to you about an important technical condition on infinite series called absolute convergence, and also about the notion of Cauchy products, which allows us to define a way of multiplying two infinite series together. Okay, so to start, let's suppose we're given two infinite series. So here we have one A, which is going to be A0 plus A1 plus A2 and so forth. And B is going to be something similar using these little b's, B0 plus B1 plus B2 and so forth. So hopefully one thing that you have seen is how you can add two series together, okay? To add two series, you get a new series and you just add corresponding terms. So the zeroth term of the sum is A0 plus B0. The first term is A1 plus B1 and so forth. But the natural question is, what happens if you want to take the product of these? Okay, so let's just do a little bit of a thought exercise and just write out what might be some sort of answer, okay? So let's just pretend that we can just expand as per usual. So what should that be? So what we do is we take this A0 and we multiply it by this series here. So what we'll get is A0 times B0, A0 times B0, plus A0 times B1, A0 times B1, plus A0 times B2, and so forth. And now that to that you have to add A1 times all of these terms. So you have to now add A1 B0 plus A1 B1 plus dot dot dot. And then you have to do that for all of these elements here, plus A2 B0 plus dot dot dot. Okay, so basically now when you want to look at this product of these two infinite series, you get an array, a two-dimensional array of products, and you want to add them all up. And so the question becomes, well, how are you going to add them all up? Now, I guess there's some choice in the definition for how to add them up, but a useful one is called the Cauchy product. And the way to sort of motivate it is as follows. So basically what we're going to do is we're going to work our way from what might be the beginning to the end, and I guess one way to do this symmetrically is to start from this corner and just to work our way down like that. So what we'll do is we'll look at this diagonal and we'll look at all the elements here. So there's only one, A0, B0, and we'll call that C0. And then we'll add these as the next two elements here. Okay, so that's going to be called C1, and then the next one will be called C2, the sum of those three elements, and so forth. And then what we've done in this process is that we've combined this two-dimensional array into a sequence of numbers. And that sequence of numbers, presumably, when you sum of these, should give you the product of these two series. So what we'll do is we'll start by making this definition. And this gives us the notion of a Cauchy product here. Okay, so let's suppose A is the sum of these AIs, as I've written here. And this B is the sum of these BJs, as I've written here. I'm going to define the Cauchy product. That's going to be this infinite series of these, the sum of these CNs. And these CNs are exactly what I've explained here. So let's write this down more formally, so you have a formula for it. Okay, so what is the nth term here? Well, let's just look and see what happens here. Okay, so here, what do you have? The indices is right at the very beginning, so you have 0 and 0. Here you have indices 1, 0 and 0, 1. They both add up to 1. Right? What are the indices here? 2, 0, then 1, 1, then 0, 2. They're all the ones where the indices add up to 2. So what we're going to do here, to look at the Cn term, the degree n term of this series, Cn, what is that equal to? So you're going to look at products of A's and B's, and which ones are you going to look at? Well, if you have the ith index for this A, then you want the complementary one, the n minus ith one for B, multiply those two, and you want to sum all of those, going from I equals 0 up to n, and that gives you Cn. And that's going to be the Cauchy product of these two infinite series. It's another infinite series. And of course, at the moment, there's no guarantee that this might converge, okay? But a wonderful fact is that if we suppose that these two infinite series don't just converge, but they actually converge absolutely, So what does converge absolutely means that not only does this sequence converge, but if you replace each of these AIs with their absolute value, okay, and you sum that, if that converges, and the same for the B's, then in fact what you will find is that you have convergence of this Cauchy product series, and it converges to what you want it to converge to, which is the product of A times B. Okay, so it's the product of this infinite sum here with this infinite sum here. And this is a rather wonderful fact. Okay, it turns out that actually you only need one of these to converge absolutely, but I've opted for this more symmetric formulation here. Okay, so maybe it's time to look at a simple example of this proposition in action so you can get a feel for what it does. Okay, so let's have a look at the following example. I'm going to look at a very simple infinite sum. It's going to be 1 plus half plus a quarter plus and so forth. It's just the sum of a GP. And I'm just going to multiply it by itself. 1 plus half plus a quarter plus and so forth. Now, of course, we know how to sum this GP. Okay, it starts with 1, and the common ratio is half, so it's 1 and 1 minus half, so it's going to be 2. So this is just 2 times 2, so this is a 4. And let's have a look and see what happens when we take the Cauchy product of this infinite series with itself. Now we'll do it the way I've written that out here, so that's quite easy to calculate these terms. Okay, so we'll multiply 1 by this thing here, 1 plus half plus a quarter plus an eighth plus and so forth. And then we'll multiply half by this series over here, so you'll have half plus you have this at 1/4, so it's the next term, plus an eighth plus and so forth. And then for the next one, you'll take a quarter of this, so you'll get a quarter plus 1/8 plus and so forth. And certainly, since all of these are positive, the fact that they converge means that they converge absolutely, so we can apply this proposition to compute this product, which is 4, as the Cauchy product. So what's the Cauchy product here? Okay, so the Cauchy product is you start with this 1 here. Okay, so that's the first term, 1 plus, and then you look at the next diagonal, so there are 2 halves. So there's 2 halves. And then what's the next term? Now you have 3 terms, and they're all the same. They're 3/4. And the next term is, well, there'll be an eighth here. 1, 2, 3, 4, 4 eighths. And then I hope you can see the pattern of what happens here. Okay, so the numerators are increasing by 1 at each stage, and the denominators are doubling at each stage. And what you have is a wonderful infinite series that now converges to 4. Now the proof of this proposition is a little bit fiddly, but I will sketch this proof for you because it shows some important ideas about how to think about such products. Okay, so let's revise our notation. So we have some infinite series here of these ANs, which sums to A, and it's also absolutely convergent in the sense that the sum of the absolute values of these ANs is also converges. I suppose this B also converges absolutely, and this B is this infinite sum of the BNs. So the first fact that we do know is that if you want to look at the product of these infinite sums, A, B, well, it's true that this partial sum, where you sum the ANs from n equals 0 up to n, that tends towards A. Okay, so let's give that a name. So maybe I'll call this AN. We'll call this partial sum A, big A subscript n. And this partial sum of the BNs, where little n goes from 0 up to big N, let's call that partial sum Bn. These will tend towards A and B, so the limit of the product of these partial sums will also go to this thing here. Okay, so this is how I want to write down this product, okay, of these infinite sums as the limit of these product, okay, the limit of these products of partial sums. On the other hand, we want to compare this with the Cauchy product. So let's look at the partial sums here. And in this one here, I'll use a capital C with a subscript big N here, and that's going to be the partial sum as n goes from 0 up to 2n. Okay, so how do you visualize what's going on here? You want to say basically that what you see here is going to be the limit of these partial sums. Okay, so let's compare this an times bn with this cn. That's what we want to do. Okay, so how do you visualize an times bn? Well, an is going to be a0 plus a1 all the way down to this an here, and b0 plus b1 all the way up to bn is going to be this sum like this. And what you do is you form this array, you multiply corresponding terms, and then what you'll get is you'll get a square array of products. And all those terms here, when you take all those products and add up all the terms, you'll get an times bn. So that's how you visualize that product. Okay, what about this one here? Okay, so remember the Cauchy product, what does that involve? You do a similar sort of thing, but now what you do is that you sum things along the diagonals. And we go from the term C0, which will be this A0, B0 term, and then the next one all the way down to where the sum of the indices is going to give me 2n. So that includes the an, bn term here, and it goes like this. Okay. So all of these terms gives me this Cn. Now what I want to do is basically say that the limit of this Cn is the same as the limit of an times bn. Another way to rewrite this is the limit as big N goes to infinity of the difference Cn minus an bn is equal to 0. And how do we visualize this difference here? Well, basically, you can see that in Cn we've added more terms than the terms that we have here. The extra terms are the ones that you have here. So for example, you have a term here which is an plus 1 times b0 and an plus 2 times b0 and so forth. And similarly, you'll have extra terms here. So the goal of the proof of this proposition is to show that the sums of these terms, as we make this big N larger and larger, the sums of those terms will go towards 0. So we need to find some sort of way of bounding how big this is and showing that even this bound is going to go towards 0. So how are we going to do that? Well, to do that, I need to introduce a little bit more notation, and you'll see now why we need the absolute convergence condition. Okay, so firstly, we're going to look at the series where we add the absolute values. Remember, we're saying that this actually converges. We'll call this, instead of a hat. Okay. Now, of course, this is at least, since we're always summing non-negative things here, this is at least as big as any of the partial sums of these absolute values. And similarly, b hat will be the sum of the absolute values. Okay, that infinite sum here. So that's the first thing that we'll look at. Okay. The second thing that we'll look at is we're going to look at tail terms of these two infinite sums. And the tail term that we want to look at is, I'm going to call it delta A, okay? And delta A, the nth one, big nth one, will be, you're going to sum up the absolute values from n equals n plus 1 to 2n. Okay, so the way you should think about this is, now let's suppose we replace these infinite series with absolute values everywhere. Okay, so this delta A n term will be the sum of the absolute values of all the ones from here down to here. And this delta B n term will be the sum of the absolute values of all the terms from here to here. Whereas the A hat and the B hat is you take the absolute values of all of these terms and you go all the way down and you sum all of them, which is at least as big as if you sum all the absolute values from here to here. And similarly, for the B hat, it's the sum of the absolute values of all the terms over here. Okay, so we want to bound the size of the sum of all these terms here. The first thing is to bound the size is that we can replace each of these with their absolute values and add them together. That will give you something that's bigger. And that basically corresponds to when you multiply the absolute values of these terms together to get those ones. Okay. And then if we're just summing absolute values, of course, if we can bound not just this region here and this region here, but instead these regions and these regions, okay, if we can bound all the products of absolute values that land in these two regions, okay, if we can bound that and show that the sum of all those goes to 0, then we'll be done. Okay, so let's have a look at the sums of all the absolute values of products in this region here. So how can we bound that? So first thing is that if we look on this side here, the product that we'll get here is basically the sum of absolute values of b0 up to bn times the sum of the absolute values of an plus 1 up to a2n. So of course, the sum of all these absolute values, okay, these b0 up to bn, okay, that's a partial sum of this sum of non-negative numbers, okay, so it is bounded by b hat. So this sum, okay, if you replace with the absolute values, is bounded by b hat. And you're multiplying it by the sum of the absolute values here. And what is this sum? This is a tail end of this infinite series. It's this one here. So that's delta A n. So that gives you the sum of the absolute values of all the products that land in this region here. And similarly, we can look at the sum of the absolute values of all the products that land in this region here. Okay, what's that? Okay, so the bound is firstly you have the sum of the absolute values of all of these terms here. Okay, and that's bounded by the sum, the infinite sum of absolute values, a hat. And then you're going to multiply that by the sum of the absolute values of the terms from here to here. And that's the tail end that we describe in this delta Bn. Okay, and now what do we notice about this? So this b hat is a fixed number, this a hat is a fixed number, this delta A depends on n, and it's a tail end. As we move further out, this is going to go towards 0. Similarly here, this a hat is a fixed number, this delta b, this n, this is a tail end. As we look at the tail of this convergent infinite series, okay, this is going towards 0. So we can see that as big N gets bigger and bigger, this sum here is actually going towards 0 as N goes towards infinity. And this essentially finishes the proof of this proposition and gives us this rather wonderful formula that if you have two absolutely convergent infinite series, then you can form this rather nice new Cauchy product series, and that Cauchy product series will converge, and it also converges to what you expect it to be, which is the product of those two infinite sums. I hope now you can also use the Cauchy product to find interesting infinite series.